Hello and welcome to Disseminate, the Computer Science Research Podcast. I'm your host, Jack Wardby. I'm delighted to say I'm joined today by Vasily Sartakov, who will be talking about his OSDI paper, CAP-VMs, capability-based isolation and sharing in the cloud. He is an advanced research fellow in the large-scale data and systems group of Imperial College London. Vasily, thanks for joining us on the show.
Thank you.
Can you start off by setting the scene for the listener and introducing your research?
Okay, first of all, I would like to tell you about my background, what I did before I started my career in research, because it defines my research topics in many aspects. I graduated from a university in 2010 with a diploma of an engineer, and I already had some operating system related experience in the industry, and my final thesis was devoted to microkernels. Since then time, I was involved in various R&D activities in the area of system security, mostly related to microkernels, microkernel frameworks, microhypervisors. I was leading a small group of engineers called XIS Labs. At this time, there was the second, maybe the third coming of microkernels. CL4 became open sourced. There were several projects from Germany and TU Dresden, Fiasco OC, L4E, G-Node framework, microhypervisor Nova. There is actually a EuroC's paper about it. It was a quite popular topic in the industry, and many people wanted to use microkernels. And our usual task sounded like, hey, we have a huge monolithic software, and we need someone who will partition it and run on top of microkernel. They usually need TCP/IP stack, network services, obviously device drivers, deprivileged graphic user interface, etc. And typical problem was the messaging interface, not only on the technical side, but mostly on social technical. I will explain. Analytic software uses jump and return interfaces between components. And when you cut them, you need to redevelop this interface to copy arguments, to redesign OPAGI pointers, callback tables, etc. This requires engineering effort, but more important, someone needs to support their sports. And this is the problem. People come, people go, nobody wants to repeat the same partitioning each time to update software. This is actually why microkernel frameworks usually have coarse-grained components. The complexity of interfaces doesn't allow to make partitioning practical. Huge components usually have narrow interfaces that are easy to port to messaging and to support later. And let's come back to my research. So in 2017, I moved to Germany and started my research in confidential computing. And in 2019, I moved to the United Kingdom. In my research from technological point of view, I'm looking how new hardware features, particularly intra-process isolation mechanisms, can be used to efficiently partition and isolate software. Speaking about operating system, it's the reverse side of medal. The part I'm interested in doesn't manage hardware, but manages software and provides primitives for isolation and sharing. The example with jump and return calls, you can use intra-process isolation mechanisms like Intel MPK or Cherry to isolate components and to create IPC primitives that preserve jump and return semantic of calls, as we demonstrated in our past year ASPLOS paper called Cubicalos. Today, we will discuss intravisor and CAP-VMs, and they also use hardware-supported mechanisms such as hardware memory capabilities to efficiently isolate components and provide efficient primitives for data sharing. Again, the isolation and sharing plus novel hardware technologies.
With all that in mind, can you describe to the listener what are the current approaches to achieving application compartmentalization in the cloud are today? What are the current approaches people take to achieving this?
The key element in the compartmentalization is the isolation technology. It defines what you can do with compartment and in general how practical the compartmentalization will be. However, despite the existence of various modern isolation technologies such as Intel MPK, SGX is also some sort of inter-process isolation with a very special threat model. The overwhelming practical solutions are based on virtual machines, hardware virtualization, and containers, namespace virtualization.
Okay, great. So what are the problems with VMs and containers?
Let's have a look on them from the point of view of tension between isolation and sharing. Virtual machines provide very strong isolation. They base it on the idea that there is no red pill, and if you have two communicating VM hosted on top of a single server, you should use TCP/IP stack and virtual networking for communication. It's very excessive because the data is in memory already, and all what you need is to give reliable access to it. Instead, we use TCP/IP for communication and data exchange. Containers, in turn, virtualize namespace, and they may use something better than networking, but the kernel is the lowest common denominator over all containers, including the host kernel, which means that your REST API application includes USB driver in the trusted computing base, or deprecated file system, or some components that you don't ever use. But this is the problem. And in other words, VM have very strong isolation, may have small shared trusted computing base. For example, microhypervisor Nova, it's very, very small, but very slow cross VM IPC. Containers, on the other hand, weaker isolation, huge shared trusted computing base, but relatively faster IPC. And what we actually need is slow shared trusted computing virtualization with fast IPC.
Okay, cool. So given the state of play and the current trade-offs you just explained, what is the key idea behind CAP-VMs?
The idea of the project is that we don't use MMU for isolation. Indeed, MMU gives you sharing and isolation, the basic technology, but MMU defines the characteristics of the compartmentalization. We have processes, we share the page granularity, and we involve a shared intermediary like kernel or hypervisor each time when we want to perform IPC.
So, I mean, can you explain to the listener what memory capabilities are?
Now we come to our basic technology of the project. So let's consider an example. You have a register, and you can load any value into it. And this register can point to any reasonable address in the address space. So you can load and store data via this register using simple instruction. But in the case of hardware memory capabilities, this register has not only the address this register points to, but also bounds of the memory that this register can point to in principle. Each time when CPU loads an address into this register, it actually loads a fat pointer with built-in addresses, bounds, and permissions. And so the CPU disallows you to reference data outside of the bounds or use this register with operations like special load or special store. Of course, you can't construct a random. You can't construct capability from a random sequence of bytes, and capabilities can be created only from another capability via capability-aware instructions.
What are the main challenges that arise by using memory capabilities as part of the cloud stack or part of a cloud stack?
Speaking about memory capabilities in the context of our paper, we of course speak about the Cherry architecture. And Cherry is a very novel, very new implementation of hardware memory capabilities. It's a hybrid architecture. It combines at the same time MMU plus capability-based isolation. And Cherry requires Portico software. If you want to get all features of hardware memory capabilities, such memory safety, you should port your software to something called Pure Capability ABI. In this ABI, all registers are capabilities and all instructions that use pointers are capability aware. On practice, it means that some low-level and system software requires some modification, and people usually don't like to change things that work. So if you have a very huge project, it will be highly likely that you need to change something into this project to make it work on top of Pure Capability API. Generally speaking, as I say, pointers become twice faster. So if you have padding instructions, if you care about alignment and other low-level things, you should change something in your software. However, compiler, an operating system provided by Cherry and people who developed this project, they're very clever. And if you don't use something low level, specific things that are aware about alignment, as I mentioned, you will not see any problems.
Okay, cool. So what are the key features then of CAP-VMs, and how do they go about addressing the challenges you just described, and how do they improve over the pitfalls of VMs and containers?
In short, CAP-VMs offer lightweight isolation, private namespace in the form of deep-rich library operating system, and fast cross-CAP-VM IPC primitives, which work at byte granularity. The latter is also important. Of course, you can share memory for communication between the virtual machines, but you should think twice before remapping pages. What if you accidentally expose something that shouldn't be exposed? Well, in case of CAP-VMs, you can give access to the data in place because sharing works as byte granularity.
Okay, nice. So let's dive into the details a little bit then of CAP-VMs. Can you give the listener an overview or describe the architecture of CAP-VMs?
CAP-VMs are managed by Intravisor. We call it sometimes as Type 3 hypervisor. It's a user-level process that uses its own memory to host CAP-VMs. The CAP-VM is just a binary executing in a constrained way. Code inside the CAP-VM can jump outside the CAP-VM only in a controlled way. This is called the host call interface, and it also can access memory outside CAP-VM bounds, also only in a controlled way. So generally speaking, you can execute any code inside the CAP-VM, but to run something practical, you of course need Linux compatible environment, and we provide it. So we have a deep privileged LKL, so Linux kernel library, fully compatibility with Linux, plus a massive libc.
Nice. So how are CAP-VMs isolated then?
Now it's a very interesting part. The isolation is a very important technical part of this project, and we fully rely on the cherry architecture. We already discussed a bit pure capability ABI, when all pointers, related instructions, and registers are capabilities, but we use hybrid API. This API allows you to use native instructions when everything is capability unaware, and selectively use capabilities and capability-aware instructions when it's necessary. Also, hybrid code is constrained by something called default capabilities. Internally, all instructions become relative to two capability registers, one data and program capabilities. Constrained code can't access data or code outside the bounds of the default capabilities, but can do this via capabilities and capability-aware instructions. So this is the mechanism we use for cross-CAP-VM IPC. In other words, default capabilities are part of a thread context. They make up a fraction of virtual address space, which means that you can create multiple compartments defined by pairs of non-intersecting default capabilities. That's how we create multiple CAP-VMs inside a single address space of Intravisor.
Nice. So what does the API of a CAP-VM look like then?
API is quite minimalistic. Just to implement proof of concept, you can instruct Intravisor to spawn a CAP-VM described by several parameters like size of compartment, binary you want to load inside, argument you pass, etc. Also, there is interface between Intravisor and CAP-VMs, so mechanisms such as creation of threads or interaction with I/O. They can't be implemented inside the CAP-VM, and the CAP-VM invokes Intravisor to provide those mechanisms. This is our host call interface. And you also can use capability-based primitives, IPC based on capabilities. We have CAP files, CAP calls, CAP stream. They also use the host call interface.
Cool. So how do CAP-VMs then avoid the need for having your application code being aware of having capability-aware application code?
Good question. Let's speak about our capability-based IPC mechanisms. Constrained code, even compromised, can access data and code outside. Constrained code, even compromised, can't access data and code outside of bounds defined by default capabilities. Also, you can't create default capabilities from nothing or increase permission of existing ones. So code is really constrained. And to invoke functions of intravisor via the host call interface, you need capabilities. And CAP-VMs have them. The intravisor stores capabilities for host call interface at the moment of creation of CAP-VMs. So now we have a CAP-VM, and there is a controlled way how you can jump outside of this CAP-VM. For that, you need to use capability-aware instructions, and you need to have capabilities. So you must use capability-aware code. However, this is the lowest low-level, like hardware abstraction layer inside the classical VMs. So this code anyway will be pure capability-aware. But we want to speak about the application code, which is always native, which means capability unaware. But capability unaware application code wants to benefit from the use of capability-based IPC mechanisms, right? And we have a transition layer, which is pure capability, and it's a driver layer. So when you have a connection between two CAP-VMs, one have a donor CAP-VM and one is a donor CAP-VM, the other one is recipient CAP-VM. The donor informs intravisor that it has memory to share, again by granularity, while the recipient probes this memory via key, like a shared memory interface in POSIX, and intravisor stores a capability to this shared memory into the memory of the recipient. So now the recipient CAP-VM has a capability to share its memory, and to use it, it should use capability-aware instructions that work inside CAP-VM kernel, as I said, like a driver. So the native code reads and writes data from the kernel objects. It's a file. And when it reads this via system call, in fact, the kernel driver invoke or uses capability-aware instructions to read data from a remote capability, from remote CAP-VM. That's all. So the separation between native and pure capability code is the kernel interface, the syscall interface.
Cool. Awesome. So can you talk us through how you went about implementing CAP-VMs and how you evaluated them? What did you compare them against? How did you compare them? And what were the key results from your evaluation?
We prototyped intravisor and CAP-VMs using RISC-V 64 Cherry-enabled platform. It's a development of people from Cambridge and the Cherry project. And we used the FPGA for benchmarks, also implemented by the Cherry team. Also, we used Hi-Fi, Sci-Fi on-edge board to test complex multi-thread services, but obviously without any security guarantees. We needed this platform to generate Docker images, so we have full compatibility with ordinary systems. So we use Docker to compile and generate images that we use as CAP-VMs. And also we tested our system on top of a multi-core CPU to obtain performance results in complex applications. Well, generally speaking, of course, our evaluation is a performance-based benchmark. We measure performance of IPC primitives we developed, such CAP files, CAP calls, CAP streams. We compare them with legacy interfaces. And the most important result probably is that if you don't need synchronization mechanisms in your IPC, you can reach performance of IPC close to memory copy speed, which is very fast. Nice. Of course, there is a not so brilliant result. If you need synchronization, you will pay for the synchronization because you need to involve the host kernel each time when you want to accrue mutex, for example, and this adds some overhead. So if you use small chunks of data and you need synchronization, our proposed mechanism is not always faster than legacy, but of course there are cases where our CAP files and CAP streams significantly outperform, like 2 times and more legacy interfaces.
Yeah, you preempted my next question now. I was going to ask you, are there any situations in which CAP-VMs the wrong or suboptimal choice, and what are the characteristics of those situations? But I guess you covered it there, unless you've got anything else to add on that.
CAP-VM, yes, of course, actually many things. CAP-VMs offer lightweight isolation and have low shared tracing computing base and have fast CAP-VM based capability-based IPC mechanisms. So, of course, we already know that there are some exceptions. There are some cases where our IPC might be less efficient than they could be, but the first and the second options, they always the first and second features, they're anyway very important. So of course, so if you don't need capability-based IPC or your use case doesn't benefit from the use of them, you anyway will have strong isolation and will have low TCB infrastructure. Another thing is, if you want to run inside the CAP-VM more than one application, this will become a little bit tricky. So it's a question in real life, will you use a virtual machine to run more than one application inside the container? Because if we have look on practical use of containers, people usually try to spawn a single service inside a single container or a VM. But anyway, so if you want to run more than one application inside a CAP-VM, this becomes slightly tricky and it will require some modification. So the problem is the transformation of pointers when you pass them between isolated compartments, like a program and the kernel, or between kernel and improviser. And those pointers should be either capability, and there will be no problem, but the code should be capability aware. Or if they're integers, so if they're capability unaware, those integers should be transferred to be valid inside different compartments. And this works with two nested compartments with the same base. When you have two compartments, one inside another one, and they have the same base, it works very well with application. This is kernel. Application can't access kernel. Kernel can access application. This works very well. But if you want to add another application, like application kernel, one of them will more privileged. One application will be more privileged than another one. This technically can be solved. So there is a solution that will allow you to have multiple native applications isolated, and there will be no need in transformation of pointers between when you pass them between different compartments. But this is the implementation isn't very optimal. This is the limitation of the architecture.
Cool. So how could a malicious user, an attacker, gain control over CAP-VM? What was the threat model you used when you were developing and designing CAP-VMs?
Very easy. We use native code, and native code is capability unaware, and it's completely and doesn't benefit from the user capabilities. So all what we have is read, write, execute bits on memory and nothing else. So obviously, if you have attack based on stack smashing, you can gain control over application, and in our model, well, we assume that you can get access even to the kernel, which is kernel technically isolated from the application. So, well, you're free to do this. So we assume that we have bugs everywhere, and our attacker gain control. However, it's not a problem because what an attacker can do, they can try to access memory outside borders of the CAP-VM, and it is impossible because all native instructions are constrained by default capabilities, and there is no way to increase permissions of existing default capabilities. Because, as I said, you can't cast a sequence of bytes as a capability. So this capability should be created by someone. And well, there is no mechanism to create a new capability for this CAP-VM inside a CAP-VM. So we can't access data outside our CAP-VM. The attacker can try to jump outside of the capability. And again, it's impossible because to jump outside capability, you need to perform capability-aware instruction, and you need to use capabilities to jump outside of the CAP-VM. And again, all capabilities that a CAP-VM has, that have execution permission, they are sealed, they can't be changed. So there is only one way to jump outside of CAP-VM, and this way is controlled. We will always go to the defined place, and the intervisor will look where you're going. And the third point, the attacker can try to access data provided from other CAP-VMs. For example, you share data and provide the CAP-VM provide the capability for that. It's okay, and then you decided to revoke this access, and you may assume that the malicious attacker won't still have access to this data because it has a capability. Again, our system will prevent this. Because the attacker can't store capabilities provided by other parties of communication. So, sounds very safe and secure.
Brilliant. So, where do you see this research having the biggest impact then? Who will find CAP-VMs the most useful? Who do you think your results are the most relevant for?
This is the research work, and we asked a research question. What does the cloud stack look like if we had memory capabilities? So first of all, we consider the research community as the target audience. Hardware accelerated IPC, but by granularity, deprivileged components with very low overhead for isolation. And we also, shown how great is hybrid code. There is a huge part of the community in the area of memory capabilities, which discourage people to use hybrid systems. So they think they try to shift more accents on pure capability code while we use hybrid code. From the industry point of view, obviously, any area that uses virtualization, but the dissemination is very limited by the hardware availability. There is a Morello board, but there's a program supported by the UK government. I don't know how easy to get access to this board for ordinary people.
Okay, cool. So, what would you say over the course of working on CAP-VMs? What's the most interesting lesson that you've learned, and maybe the most unexpected thing you've learned while working on this project?
Well, to be honest, I was very constrained in time, so I had no time for lessons. But at the same time, I was very surprised when we moved everything from QEMA to FPGA board, and everything worked out of box without any change. So it's a quite unusual practice when you do this.
Yeah.
The Cherry team had been doing a great job. On the technical side, there was a moment when I realized that I'm actually benchmarking TLB, but what I expected to benchmark. So low-level benchmarks are very tricky and require a lot of attention. So you always must be sure that you're benchmarking what you are going to benchmark, but not something else. So I got very, very, very wrong numbers. I didn't understand why in one case I have, let's say, 2x performance, in another case 5x performance benefit, and only after some very long investigation I accidentally realized actually it's because of TLB. We have different addresses and they have different performance impact.
Nice. So obviously, progress in research is very non-linear. So, from the conception of like the initial idea to the actual end, the publication, were there things that you tried that failed, and were there other things that maybe you could, certain dead ends you could explain to the listeners to kind of so they don't end up making the same mistakes that you've done?
This project is complete. There is a story, design, implementation, benchmark, and it has a finished set of features. So, well, people in research know that sometimes to sell an idea, you need to add several features to make reviewers happy. And after first rejection, the second, people add more and more features, making a project more and more complicated while didn't change the original idea. So in current state of the project, it's incredibly complicated to add something into it from the point of view of features. Otherwise, you will break something else. For example, some may say that people may want pure capability CAP-VMs, while we have hybrid CAP-VMs. Actually, Intravisor already supports pure CAP-VMs, but the use of pure CAP code breaks the revocation story. So you can't revoke shared capabilities using the method we introduced in the paper. So we had several forks on the road, do you want to pass pointers between isolation layers as integers or capabilities? Because this defines, do you need to redevelop the interfaces or you can use all what you have? Do we want to add capability-aware calls or use just what we already have? It's actually, I began my presentation today. I said about jump and return calls at the beginning of our discussion, and it's exactly the example about the problem and the possible decision. So another question is, do we need revocation of capabilities or not? And finally, are we capable to port huge software like LKL to pure capability architecture? So depending on the decision, the implementation will be completely different. And the story as well also will be different. And it's hard to say that all other decisions are scientifically wrong, especially given that in systems, the scientific criterion is performance. If one can find a way how to easily port LKL to pure capability or deal with CAP revocation in pure CAP code, this will be a great project, a great paper. The revocation problem actually is a very well-known problem in the field of hardware memory capabilities, while porting of huge low-level system code is very challenging, but also depends on resources you have. But, well, maybe people can find something more easy way to do this.
Nice. So kind of building on that, like I know you said this project is kind of finished, but what do you have planned for future research?
We are working already on the next project. It's also related to the future of cloud computing. It uses the conception of CAP-VMs. This try we will try to overcome some drawbacks of pure CAP code, but the project is in a very, very early stage. So
okay,
cool. Don't have many information about it.
Sure, no problem. So I know you kind of talked us through your background at the start, but what kind of attracted you to this research area, and what do you think is the biggest challenge facing it now?
I do like operating systems, and I have been working in this area for many years, and it suits my skill set. Also, I like to use fancy hardware features to improve software systems. However, it's relatively complicated to conduct research in the field of operating systems. I want to say that this is challenging not because of scientific side, but more about the gap between existing research industry and the way how the research community accepts the ideas. There is a keynote from ASPLOS 21 by Timothy Roscoe, and he described this problem very well. So I recommend to everyone to have a look at it. Long story short, the systems research in general and operating systems in particular are very problem-oriented. That's why we see performance-based justification of scientific results in every first paper. And because the overwhelming amount of software lives in 19s with monolithic Linux, and that's why people want to see solutions which are compatible or comparable with Linux. Instead of moving to new technologies invented in the last 20 years, people deal with old things that just work, but researchers don't know how, on the one hand, to propose and other solutions to problems that they already have been solving for many years, and nobody uses them, or try to convince people with very crazy ideas that can't be compatible with Linux and expected set of benchmarks and software.
Cool, awesome. So time for the last word now. What's the one key thing you want listeners to take away from your research on CAP-VMs?
Hardware memory capabilities introduced in Cherry not only solve problems related to memory safety, but can be used to build low overhead, highly partitioned cloud systems.
Fantastic.
Software, actually, it's not only about clouds.
Perfect. Well, we will leave it there. Thanks so much, Vasily. If you are interested in knowing more about his work, we'll put links to all his relevant materials in the show notes. Thanks for listening, and we'll see you all next time for some more awesome computer science research.